Hey everyone, welcome to Earth and Space Science today. Glad that you guys are here, and I'm sorry that I could not be there today. Today we're going to be talking about the last piece of evidence for the Big Bang Theory. Okay, so I don't have a whole lot of notes for you today. I have one slide, and there's one video that you'll watch that's already been posted to Schoology. So watch that after you watch this presentation here. So we are in the astronomy notes. So if you go to the purple folder and you scroll, well, actually it's at the top of the purple folder on Schoology, you'll find our notes for astronomy, and then if you scroll down to the very bottom, you'll find our slide for today. Now, just be aware today when you're watching this, this is the title slide, which is actually the first slide in the presentation. I've moved it around as well as one other slide. I've just moved them around so that way I can make this quick presentation a little bit easier without skipping through a bunch of slides. So, anyway, astronomy is where we're at today. And we are going to be talking about the Big Bang. So, we're going to be talking about evidence for the Big Bang and the last really key piece of evidence that we'll be covering in this class. Be aware that the Big Bang Theory is controversial, and at least it tends to be controversial. But it is the best explanation. The Big Bang Theory is the best explanation for the beginning of the universe that we have so far. Okay, does it answer all of the questions? No, but as far as scientific evidence goes, the Big Bang Theory is the most scientific theory for the origin of the universe. Okay, it's not the only one. There are other theories out there. This is the one that we're covering in class, the most scientific one. Okay, let me click on over to the next slide. Here we've seen this. I've shown this slide to you plenty of times now. These are the 6 key pieces of evidence for the Big Bang Theory. Number 1, universal expansion and Hubble's law. The universe is expanding. We can measure it today. Okay, and it's bigger today than it was last time, and so it makes sense. It's logical to say, well, okay, if it's getting bigger every day, then if we just hit rewind and we go backwards in time, instead of getting farther apart every day, things would just be getting closer. And that if we plug things into some sort of simulation, that's exactly what happens. They come together. A point. Okay? Hubble's law tells us how they're moving, how fast they're moving, and the speed that they're moving, but really they're moving away from everything else. So if we just turn that around, logically, you'll see that they come together at a single point. They're all coming back together if you turn it around. Okay? Number 2, cosmic microwave background, the 3-degree background radiation. We predicted it before we could measure it. We predicted that it should be there. And once we could measure it, it turns out our predictions matched our findings very, very closely. That means we're on the right track. Those two together are probably the best evidence for the Big Bang. Number 3, number 4, number 5, good evidence for the Big Bang because it tells us how the universe is changing over time. How has the universe changed? Well, in the early universe, quasars, the conditions for creating quasars was much more prevalent. It was much more hospitable for quasars. It was easier for quasars to form. The conditions were right. Today, that's not the case. We don't see quasars in our part of the universe not because they couldn't possibly form today, but just because the conditions are not right. The universe has been changing over time. Okay, and the farther away that we look from us, the farther back in time we look, the closer to the beginning of the Big Bang, the beginning of the universe that we look, the more quasars we see. Radioactive decay tells us that things are really old. And if things are really old, the universe has to be at least as old as them. Now, the Earth, we find rocks that are 4.2 billion years old. But we found rocks that are much older than that come from space, that come from outside of our solar system. We have found them. We have found them on Earth. They have crashed into Earth. Meteors and meteorites. Okay? The oldest ones we have found are like 7.2 billion years old. That tells us that the Earth is at least not the Earth, I'm sorry. That tells us that the universe is at least 7.2 billion years old. It has to be because we have things that are that old in the universe, which disproves a popular theory where the Earth and the universe is very young. radioactive decay. I'm sorry, I just covered radioactive decay. Stellar formation and stellar evolution. Tell us, and this is the one that you just did, that star in a box. So stellar formation and stellar evolution tell us something about the timeline. Again, this is talking about how long does it take these stars to form. When you filled out that table in part C of the star in the box, part of that was filling out the total lifespan of a star. How long did that star really live? And what you'll find is it's millions or billions of years. The universe has to be that old. We see the stars evolving over time, right? And not only that, but we see the nebulas, and we see like those nurseries for the stars, and how the elements are compounding, especially the heavier elements. Now the elements, everything above hydrogen and helium, requires these stars to live. And not just live, but everything above iron requires these stars to die. Okay? So it's living and it's dying, and then we have generation after generation after generation of these short-lived, high-energy stars that are going supernova and supernova and supernova and adding all these elements to that cloud, to that nebula cloud. And it's growing and growing and growing. Without all of that, we would not have the atoms, we would not have enough atoms to create our bodies, or to create the desk that you're sitting on, or table that you're sitting at, or couch that you're sitting on, or whatever. The Earth, there wouldn't be enough molecules, enough atoms to create the Earth if there was not generations, countless generations of stars forming and dying, creating them. Okay? Number 6, this is what we're talking about today in class. This is what our slide is over. Number 6, the speed of light and stellar distances. Okay? The speed of light will tell us something about the Big Bang. All right? And it's really the stellar distances, I think, that's the really important one. But here we go. The speed of light is universal. The speed of light is constant. Okay? 300,000 kilometers per second. That's a constant speed. Okay? And it doesn't matter if, if your spaceship is flying at 299,000 kilometers per second, and you turn on your headlights, that light's going to be traveling at 300 kilometers per second. It's constant. Okay? That was kind of a dumb analogy, but I think it'll make sense later. I'll talk about it later. If you think back to E equals mc squared, that famous equation, E equals energy. E is energy. E energy equals mass, m, times c, the speed of light, squared. E equals mc squared. C is a constant, 300,000 kilometers per second. 670,616,629 miles per hour. That's fast. 186,000 miles per second. 299, almost 300,000 meters per second. It's just shy of 300,000 meters per second. That's fast. Anyway, the speed of light is extremely fast. So we observe these stars that are millions or even billions of light years away. Very, very far away from us, okay? And we measure the distance between us and these stars using something called a light year. Now, when you think of light year, a lot of people will think of a time. A light year. Well, year is the distance of time, but a light year is actually the distance, a measurement of the distance that light travels in 1 year. Okay, so you could use a ruler, a meter stick, to measure a light year if you were so inclined to do so. You wouldn't be able to finish in your lifetime, but you could. The light that we see today from a star that is 500 light years away is 500 years old. And I've talked about this before with Proxima Centauri, which is one of the closest stars to us. It's about 4 light years away. That light left the star 4 years ago, which means like when we look at it, we're looking 4 years into the past. The one that I used in class previously is if we looked at a star that was 65 million light years away, we wouldn't see it the way that it is today. We'd see it the way it was 65 million light years, or 65 million years ago. The same way that if they were looking at us right now, some intelligent being on that star, that planet that's 65 million light years away, they wouldn't see us. They would see dinosaurs. The demise of the dinosaurs, maybe. Right? They wouldn't see us. We would miss each other. Even though we're alive at the same time, we would never know it because we couldn't send signals to them. We couldn't see them. It's too far away. It's looking back in time. I think that's really crazy and really important to understand. So the furthest stars, the very farthest star, the very farthest galaxy from us is this MAC S0647-JD. That just rolls right off the tongue. What a great name. It's 13.8 billion light years away. It's as far as you could possibly get. Now it's rounded a little bit. It's rounded, so you'll see 13.7 something. That's the farthest away from us that we can see something. Okay, when we look at MAC S0647-JD, we don't see the way that it is today. We see the way it was 13.8 billion years ago, or 13.7 billion years ago, depending on how you round it. It formed just after, not even a half a billion years after the Big Bang. It formed shortly after the Big Bang. Okay, and so we see it with about 1 billion stars. There's about 1 billion stars in this galaxy. That's the farthest away. It's crazy. Now, we have telescopes that can see much farther than this. Our telescopes can see a lot farther than that. Okay? But when we look out there, there's just nothing there. There's nothing to view. There's no stars out there. There's no visible light out there. Okay? So there's a few different theories of why this could be. One, maybe there's a hard boundary, like a wall, the inside of a bubble. And the bubble is expanding, sort of like this. The bubble is expanding, but there's this wall here, and everything's inside. All the galaxies are inside, but there's this wall. Maybe that's the case. There's just this wall there. Okay? I don't think that's true, because if that wall was there, you landed here, couldn't you just climb to the outside of the wall? Somehow get to the outside? And if you could, is that really the boundary of the universe, or is there more universe beyond this? What's beyond that? I don't think that's a very good explanation. Another idea is that the universe just doesn't end. That just goes on forever. And yeah, okay, so the farthest galaxies might be 13.8 billion light years away, but maybe there's just nothing beyond that. It's just vacuum of space, just emptiness. Maybe. But I think the better explanation, and the most scientific explanation, is the Big Bang Theory. The universe just doesn't exist beyond that. Not because there's some hard wall, but because as we look 13.8 billion light years away, we're looking back in time. There's just nothing there to view. The universe just doesn't exist. Now, I don't know which one of those is correct, but the one that seems to make the most sense, that has the most evidence, is the Big Bang Theory. Okay? The idea of looking back in time. Now, talking about the speed of light, I'm going to cover this again in class next time. I have about a minute left in this video. There's a great video by a guy named Carl Sagan. Okay? I've already linked it in Schoology. It's at the very bottom of the astronomy folder. I don't remember. It's something about the speed of light, and if you hover over the link, it'll say Carl Sagan at the end. Go watch that video now. Okay? Go watch that video. You have no homework. As long as your star in a box assignment is turned in and you have no missing work, then that's what I got for you today. If you have missing work, star in a box is not done, or you have some other missing assignment, email me, talk to me. Okay, let's at least keep me informed and let me know that it's going to be late. Right? I want to communicate with you. A big part of this is communication. Communicate with me, and let's work out a plan to get it done, because I want to help you. I'm here to support you, and I'm here to help you. Guys, have a great day. Enjoy your weekend, and I will see you next week.